Good evening to all of you. Can you hear me?
Yes, sir. We are hearing, sir. And
And you can
your screen share is also visible.
Okay, fine.
Thank you, sir.
So, very good evening to all of you. And
Sir, we will introduce you, sir.
yes, please.
Sairam, you please post YouTube link also.
Yes.
Uh, Good evening, all of the participants. Sir, a few more participants will join. It is early at 6:56. Anyhow, I request today, actually, we are very glad that Professor Rajiv Sharma, sir, from Professor at IIT Madras, he he has the main role in our workshop because he is around taking 30% of the classes. So 3 classes today, tomorrow, and next day of tomorrow that he is taking one more class. So today he is giving advanced concepts in hydrodynamic design. Sir, yesterday, day before yesterday, first day, Dr. H. N. Das sir given introduction on computational fluid dynamics. And yesterday, Dr. T. Venkatratnam, technical officer NSTL, he given introduction about condition monitoring. 2 sessions went very nice, sir. And you will be added to this August gathering. And now I request Sairam to introduce our today resource person, Professor Rajiv Sharma. Thank you, sir. Over to Sairam.
Thank you, sir. It is a great pleasure to introduce our speaker of today's program, Dr. Raju Sharma, sir. Dr. Raju Sharma is currently working as professor in the Department of Ocean Engineering at IIT Madras. He completed his BTech in Civil Engineering from IIT Roorkee, MTech and PhD in the Department of Ocean Engineering from IIT Kharagpur. His areas of interest include design of deep water drilling solutions and floating structures, computer-aided geometric design, computational geometry, visualization and their applications in design, robotics and manufacturing, dynamic data-driven forecasting system, etc. He has guided 7 MS students, 3 PhD scholars, and currently 7 PhD scholars are working under him. He has more than 50 research papers to his credit, published in national, international journals and conferences. He has organized several short-term courses, workshops, international conferences at IIT Madras. He has received research grants from Institute of Drilling Technology, ONGCL, Marine System Panel, Naval Research Board, DRDO, Industrial Consultancy and Sponsored Research, IIT Madras, and several other agencies. Now I request Dr. Raju Sharma, sir, to take over the session.
Thank you, Sairam. Thank you, sir. You please take.
So, when I was invited to deliver some talks in the short term course, I was a bit surprised because I normally do not work on hydrodynamics per se, but we do a lot of hydrodynamics when it comes to design, and especially when it comes to design of hydrodynamic systems. So, this talk and tomorrow and day after also, a lot will be on how a particular concept from hydrodynamics or from structures or from computing is basically related to design. And when it comes to design of underwater systems, there are a couple of systems which comes in our mind. One is autonomous underwater vehicles, submarines. The difference is that when you talk about hydrodynamics, you think either the body is submerged or the body is floating. If it is submerged, then how close it is to the free surface. So, broadly speaking, these three classifications. That means when the body is floating with the free surface, that means you have a free board and you have depth of submergence. That's where you find the boats, you find the ships, and all that. Then you have autonomous underwater vehicles, which will operate very close to the surface, very close to the mean sea level, and depth of submergence will be low in general. The third class of system is submarine, where we have a lot of expertise and we have done a lot of work for Indian Navy for the defense. So when it comes to hydrodynamics, the concept of hydrodynamics are mixed with structures. Otherwise, you cannot use them in design. Similarly, when it comes to hydrodynamics, you have to combine the hydrodynamics with the shape, hydrodynamics with the velocity, and hydrodynamics with the fluid medium in which the body is running or the body is floating or the body is operating. So broadly, whenever we talk about any structure, we think in terms of in which environment it is operating. If it is operating in air, the density and viscosity. If it is operating in water, density, viscosity, and the free surface effect. We do not have free surface effect when we talk in terms of air. So aircraft industry doesn't talk about free surface. They do talk about the temperature variation, the air at slightly colder temperature, at slightly hot temperature, and all that. They talk about that, but they don't talk about free surface. The complexity in the world of naval architecture or in the world of ocean engineering is primarily because of the free surface effect. And this free surface is interesting because above the free surface, you have air. You have air mixed with water and trapped. You have wind, significant wind forces. And when you go deeper and deeper, then you have the hydrodynamic pressure, the hydrostatic pressure coming into picture. Very close to the surface, you have all the hydrodynamic effects which come into picture. So our interest, and in general, when we talk about underwater systems or ships, is to understand all these three concepts. That means what happens when you are close to the free surface? What happens when you are slightly away from the free surface with low depth of submergence? And what happens when you go extremely deep and when you think in terms of 1000 meter, 500 meter, 3000 meter, like that? The lowest point on the planet Earth when it comes as far as the ocean depth is concerned is approximately 11,000 meter. That's Marina Trench. So suppose a body want to go there, a vehicle want to go there, and it should be able to withstand that much hydrostatic pressure. So that's where the structure comes into picture. So it is our firm belief, and normally we advocate this very forcefully, that in the world of naval architecture, in the world of ocean engineering, we should not think hydrodynamics in isolation. We should think hydrodynamics combined with structures. We should think hydrodynamics combined with all other components which come into picture. Because if we just think hydrodynamics just as hydrodynamics, it will not be usable in the design. And if you cannot relate any aerodynamic concept to design, then it basically remains lecture for the sake of lecture, research for the sake of research, theory for the sake of theory, knowledge for the sake of knowledge. So we advocate this very strongly, that whenever you talk about hydrodynamics, try to think in terms of how hydrodynamics is combined with the structures, because we are essentially talking about dynamics of waves, dynamics of current, and all of them give rise to what we call fluid structure interaction. That means FSI. So you have a force which comes because of the wave, and when you have wave, when you have velocity, it becomes an impact. Current, if you are close to the surface, the current forces are very high. As you go deeper and deeper, the current velocity will start coming down. So when you are very close to the sea base, the current velocity will be zero. And when you are close to the surface, it will be around 1 to 2.5, 3 meter per second. It's pretty high. So we need to think all these forces. And then how do you take these concepts into design? So this lecture will be today, and if possible, we'll discuss about it tomorrow also. Some part like how the high performance computing is used in design of underwater systems. So first, we will briefly talk about what are the types of underwater structures, what are the type of underwater vehicles, why submarine is so important, what are the loads acting on submarine which come because of hydrodynamics, and what are the hydrostructural issues in submarine design. The idea to explore ocean is very long. It started with Aristotle in the Greek history. So it always fascinated people. People wanted to see what is inside the ocean, what is deep inside, what is close to the surface. So initially it was all about transportation, and later on the transportation gave rise to ocean mining, then ocean energy. So first few concepts in the area of hydrodynamics were all about ship, which are primarily used for transportation. Then the hydrodynamics evolved for the underwater vehicles because the idea shifted from exploration to survey to mining, and that's where the ROVs, remotely operated vehicle, autonomous underwater vehicles, submersibles, all these came into picture. And now the focus is on energy. So now let's think about these three areas per se. When you talk about ship, we do not normally talk about the wind forces because ship doesn't have much area exposed against wind, except when you talk about container vessels, because container ship will have a lot of containers stacked on the deck above the free surface of the load water line, and that will give you significant area exposed to wind. Similarly, the ships which have large freeboard, for example, tankers, LNG ships, they also are exposed to wind. So you have wind forces significant. But other ships, and in general, most of the ships will not have too much area exposed against wind. But when you talk about wind turbines, offshore wind turbines, then you have a lot of area which is exposed to wind. Then you also have a lot of length which is extending from the base onwards. So that act like a cantilever. And cantilever, when exposed to wind, when exposed to all kind of forces, will have very high bending moment at the base. So ship will not have much to do with wind. Turbines, wind turbines, offshore wind turbines will have a lot of issues with the wind. Waterways will affect both. When it comes to underwater vehicles, they are launched from the mean sea level. That means the surface effect comes into picture. They will try to remain close to the mean sea level. Depth of submergence will not be very high, except for submarines where the depth of submergence will be very low. So you have all effect coming into picture. Hydrostatic pressure is coming into picture because it is operating at a very large depth. Hydrodynamic effect are coming into picture because it is close to the surface. So now you think ship, autonomous underwater vehicle, and the turbines, wind turbines. Wind is coming into picture, wave is coming into picture, current is coming. So underwater vehicles are the areas where primarily the wave force will come into picture, current velocity will come into picture, and the depth of submergence will come into picture. Now, NSTL has a lot of experience in this area. They have their multi-hull AUV, which they have designed and tested. Their experience shows that it depends a lot on the sea condition, when you want to launch, when you want to recover. And this recovery and launching mechanism is something which can go horribly wrong if the sea states are not favorable to you. That means if the hydrodynamics or the basic hydrodynamics is not favorable to you. So this is something which we need to understand, that When we launch a vehicle or when we want to recover a vehicle, it is important for us to know in what sea state we are operating. When the ship becomes larger and larger, the effect of sea state actually starts reducing. So if you have, for example, a big aircraft carrier around 300, 400-meter long, then it can actually run through a hurricane. Uh, it really doesn't affect its performance much. But when you talk about small vessels, especially when you talk about boats, then it's not advisable for you to run the ship or the boat when the sea states are not favorable. So underwater vehicles, especially when it comes to submarine, they have a long history. The first use, or first you can say the documented use, was reported in the Civil War of America, the Confederate States of America. That is the other idea which was proposed in opposition to the democratic idea of United States of America. So one force was led by President Abraham Lincoln. The other forces were from the Confederate States of America. So they were the first one who used, and it was a called turtle submarine, human power. Later on, 1900, the first idea was proposed for gasoline electric power. In World War One and World War Two, German and US submarines were proved highly effective. Combination of, for example, USS Albacore teardrop hull shape and nuclear propulsion gave rise to the modern submarines. Now, there are two issues here. One is the teardrop hull shape. So this we will talk in detail that why the shape is very important when it comes to hydrodynamics. How the shape is affecting the drag and how the shape is affecting the power. Now, we need to understand this very clearly that you may have a low drag, but the low drag may not give you the low power. So, conversion of low power to low drag or from low drag to low power is something which is not really well understood. Most of the bodies which gives you very low power may not give you low drag. Bodies which give you low drag may not give you low power. But the overall idea is to optimize or minimize the power required, not really the drag required. Now you have a body for which the weight is supported by buoyancy, the simple principle of Lambda actually. Thrust is to be delivered by the propeller. Now propeller is attached to the hull, so you have hull propeller interaction. And this hull propeller interaction is something which converts the drag to power. So the overall idea is to minimize the power, but we also minimize the drag because it's a step by step process. Normally, if the drag is horribly wrong, the chances of getting very good power reduces significantly. So we start with low power or we start with low drag and then we include the hull propeller interaction and then we try to minimize the power. So this low drag is something which is related to shape. And that's where the shape investigations started. Submarines, autonomous underwater vehicles, remotely operated vehicles, all of them have significant component which comes from the shape. So teardrop is one kind of standard shape which has been evolving over a period of time. Now, when it comes to the use of underwater vehicles, when it comes to the use of submarines, Navy looks for indefinite underwater endurance. Commercial industry will use only submarine. Some sorry, Submersibles. So submersibles means you have limited endurance. When it comes to submarine, you talk about endurance which is extremely long. That means for a couple of months, for a couple of years. And that's where the nuclear propulsion came into picture because when it is nuclearly powered, the endurance goes up significantly. Also, the deeper you go, you don't have effect of waves, you don't have effect of currents, so the environment becomes very calm. What is important when you design underwater vehicles? Don't think in terms of cost because they are going to be expensive anyway. When it comes to Navy, the cost importance reduces further because Navy wants something which is costly but cannot be detected. So stealth characteristics comes into picture. And the idea of an underwater vehicle, when it comes to the design, the concept will come from both surface ship and aircraft. Volume optimization, the weight optimization, how the weight should be distributed, comes from the aircraft. The free surface effect comes from surface ship. Now, what is the importance of hydrodynamics? It is important because we are talking about a medium which is highly viscous. We are talking about a medium which is having a velocity in terms of current. We are talking about a medium which is also generating waves with a particular fluid. You also have a fluid which is influenced by the wind, so that's where the waves comes into picture. You also have a fluid medium which is influenced by the gravity pulls. That's where you have the tidal waves coming into picture. So that means whatever complexity we can think of, current, wave, tides, ice, is actually there in the field of hydrodynamics. And when it comes to hydrodynamics of underwater vehicles, it gets further complicated because all three operations are coming into picture. Surface, slight submergence from the surface, and deeply submerged from the surface. The teardrop shape, and the teardrop shapes look like this. And we will see how this shape can be thought in terms of basic mathematical model. And the idea is that normally the human tears are very full, or any tear is very full around the nose. Then it starts reducing in terms of diameter. And finally, you have a tail which becomes a pointed tail. When the hydrodynamic investigation started on this shape, what was concluded is something very interesting. It emphasizes hydrodynamics over the other areas. That means stability becomes less important. The drag, the pressure distribution, the, the fluid particle velocity distribution over the hull, all these become important. Then stability, structural deformation, etc. So teardrop shape emphasizes hydrodynamic flow above all other factors. So ideally, if you look at purely from the perspective of hydrodynamics, teardrop shape is the best one. What is the benefit? The increase underwater speed. It means if you want to launch a missile, if you want to launch a torpedo, if you want to launch any other underwater weapon, if you want to design a torpedo, if you want to design a autonomous underwater vehicle, running at certain depth of water, certain depth of submergence. In that case, the speed gain which you will get by teardrop shape is significant. What are the other advantages? The speed is high, but also the, the signature, acoustic signature, is small, which also is very important because if the acoustic signature is small, that means your vehicle, your system become undetectable. And that is very important for the Navy. That is important for all kind of naval systems. So a smaller acoustic signature is preferred because it allows you not to get detected. Sonar comes into picture because when we talk about underwater, we have only sound as a way of communication. So acoustic waves are the only way of communication. Now, when it comes to acoustic communication, there are three issues which we must always remember. One is that the losses are significant. Water waves, sound traveling in water, can get influenced by a lot of noise. So, signal to noise ratio is adversely affected. If you start with two, three acoustic modems, most of them will fail. So, you will have only one or two surviving. So, failure rate is approximately 40 to 60% in this field. Noise is too much coming to system. So it's difficult to rely on acoustic communication. But the issue is that underwater you cannot have electromagnetic waves. So we have to be acoustic. But the field is still evolving. So the most difficult area in the underwater communication is how to get acoustic signatures right, how to interpret them right. Just another field of research. The another advantage of this teardrop hull or the teardrop shape is that entire bow could be used to house a sonar, sound navigation and ranging, sonar full form, for the submarine's own hunting of opponents. The forward hydroplanes are located aft of the sonar array or on the sail, that is the conning tower in older boats, so as not to interfere with the sonar. So now think in terms of the the shape parts. This is nose, this is tail. From the naval architecture convention, this becomes the forward part, this becomes the aft part, this becomes the middle part. Now, in general, when we talk about ships, when we talk about boats, when we talk about any body underwater or close to the surface, what is actually happening? So, a couple of observations we need to understand in a proper context. The size and speed is increasing. Now, one can ask that why it is important in the field of hydrodynamics. Now, think about it. The speed is increasing, the drag will increase. So, it shows a exponential increase. So, if the speed is increasing, the drag will start rising. Size is also increasing because when you transport large area or large volume or large weight, your cost per unit transportation reduces. So it is important for you to design a ship which is as large as possible because in that case, the unit cost will come down. So because of this, size is increasing, speed is also increasing. Initially, we had a is seen where ships were designed, especially the container ships of around 0.6, 0.65 block coefficient. Now you have ships which are being designed at 0.7, 0.725. There was a time when tankers were designed for around 0.8. Now tankers are designed around 0.875, touching roughly 0.9. Larger lengths are around 400 meters nowadays of all the big ships, container ships, and the tankers. The power sources are different. So now we have diesel electric propulsion, diesel propulsion, gas turbines, nuclear propulsion. Now, diesel propulsion is used for most of the commercial ships. Diesel electric is used for submarines. Gas turbines are used for LNG carriers. Nuclear propulsion is used for submarines or the aircraft carriers. So, whatever power source you can think of, it has application in the field of ocean engineering. It is also affecting the hydrodynamic design because when you have diesel electric or when you have electric system, then this system need to come close to the surface, close to the mean sea level to get the oxygen supply. When it comes to diesel propulsion, then you have to design the motors, the gearboxes properly. So it becomes a propeller integrated with rotary systems. Improvement in propulsion and materials is expected to bring down the cost in transportation. It is also expected to improve the propulsion efficiency. So, what we are trying to understand is that you have a propeller running at certain RPM in a particular fluid of certain viscosity and density. Now, what are the hydrodynamics load coming on the propeller? How the propeller performance can be improved by looking at the propeller design. Apart from design of propeller and the idea to change the pitch, diameter, changing the pitch to diameter ratio, controllable pitch propeller and all that. We also need to look in the way the propulsion system is designed. Materials, if you are using propeller of a certain material, what happens if we use aluminum? What happens if we use alloy? What happens if we use ceramics? Stealth characteristics depends upon both hydrodynamics and the structure. So here the fluid structure interaction comes into picture. Improvement in the operational capabilities, for example, attack, defense, and rescue. All of them is strongly influenced by the hydrodynamics. For example, if the drag of the body is very large, it cannot be used for attack because the velocity achieved will be low. Suppose you want to use a body for defense, that means something has gone wrong, you want the system to be recovered. Again, it cannot be used if it cannot go deeper and deeper. Similarly, rescue operations. So, how deep you are, how fast you can go, how slow you are, whether the fluid density is on the larger side, on the lower side, all this affect the design. Now, one can argue that what is the difference normally in the density? Now, that's something which is very surprising because you may have a freshwater lake, you may be running in sea, you may be running in river, and the density of river water will be significantly different from density of lake, density of seawater. So we may have 1025 kg per meter cube. We may have less than 1000 kg per meter cube. So, for example, we may have water entrapped with air. We may have water highly polluted. Now, a body which is expected to be operating only in the submerged condition, the buoyancy is determined by the volume displaced. And for a body which is fully submerged, the volume of the body is the volume of the fluid displaced. Now, the same body, when it runs in sea, when it runs in lake water, when it runs in river water, will have different buoyancies because the density of the water in which it is operating is different. Now, the weight is not going to change because you cannot have one weight of the structure to be running in seawater, one weight of the structure to be running in lake. That means for underwater systems, for underwater vehicles, you should have some idea by which the variable buoyancy is accounted for. And this variable buoyancy is coming because of multiple reasons. One reason is that the seawater density is different or the water density is different. Second, if you want your vehicle to go down, in that case, the weight should be higher than the buoyancy. If you want your vehicle to come up, the buoyancy should be higher than the weight. If you want your vehicle to be operating at a certain hovering depth, that means you just want a capability to hover, maintain a constant depth. That means the weight is equal to the buoyancy. So, how you consider hydrodynamics into design of a variable buoyancy system? That's a very active area of research. A lot of research has gone into it, and still, whatever design solutions are available, they are available for a particular depth and a particular capacity. All the major navies in the world will have submarines. All the major navies will have autonomous underwater. Not all will have aircraft carriers. So, which tells you that what is the importance of submarines, what is the importance of underwater systems, what is the importance of underwater vehicles in the naval contest. Now, we were talking about shapes and we were talking about roughly the size, roughly the kind of aerodynamic forces which are coming into play. Now, let's see the evolvement of the underwater vehicles, primarily the evolvement of submarines. Now, this is the propeller, this is the sail, this is the deck from where the missiles are launched. This is also the place where the missiles are stacked. Now, again, let's think in terms of basic approach to design. This is nose, this is tail. Tail is finer, nose is smaller. In general, if we look at the nose, it is important from the drag point of view. In general, when we talk about tail, it is important from the propulsion point of view, stability point of view. When we talk about the middle body, it is important for the payload, for the volume, for the area. So maximum volume, maximum area will be available in the middle part. Nose is important because that's the area where the flow will open. Sail is used for communication. Sail is also used for oxygen supply. So this is the area which is likely to come very close to the sea surface when the submarine needs oxygen. So most of the pictures of submarine which you see, you will see this part is exposed. So it is coming close to the, and some part is exposed, some part is under submerged. Now, a typical submarine may have displacement which is greater than many surface ships, but relatively big. You can see the height of submarine touching approximately 70 feet, diameter touching approximately 42 feet, and the submerged displacement is around 18,500 long ton. And one long ton is slightly higher than the ton. Other Los Angeles class submarine of US Navy, you will see the sail has shifted slightly away from the nose. And this also tells you a very interesting thing. When it comes to ship, you can think of ships in terms of few standards. So you will have one class of container ship, one class of ultra large crude oil carriers, one class of very large crude carriers, and they will have standard design. And company may order five of them, six of them, 10 of them, like that. When it comes to underwater vehicles, when it comes to submarines, when it comes to remotely operated vehicles, so in the area of underwater vehicles, we normally do not design something in a standard fashion because every vehicle is designed for a very specific purpose, for a very specific application, for a very specific set of requirements. So when your design requirements are distinct, when your design requirements are different, it is not possible for you to have a standard design. So depending upon what kind of stealth characteristic you want, what kind of signature profile you want, what kind of waves current you are expected to encounter in your operational history, all will affect the design. So it is less important for you to think in terms of standard design, standard approach when you are dealing with underwater vehicles. See the length, 360 feet. The height is 50 feet. Diameter is 33 feet. And the submerged displacement is only 6,900 long ton. One more, submerged displacement is 6,900 long feet. Length is 360 feet. The total height is 50 feet. And the diameter is 33 feet. Now, the difference are the bow plane, the sail, is changing the location. So when we think in terms of hydrodynamics, then we do this investigation that for a payload, for a particular set of design requirement, what is the ideal location for the bow plane? This location will be somewhere close to the nose and the middle portion. You will not be putting this somewhere here. You will not be putting this somewhere here because that's the area where you have the propellers running. And propeller will create noise, propeller will create the vibration. So this need to be placed very close to the nose, not very close. That means not at the nose itself because that's where the flow will open. Angle of entrance of the flow will come into picture. So their location, their shape, their size, everything will change depending upon the requirements of your design. Again, one more example, 352 by 7.75 feet. The height is approximately 60 feet and the diameter is 40 feet. Now, what is the difference we can notice is that the change of height to diameter ratio is dropping. So previously, they were designed for a very high ratio. That means the height was on the higher side, diameter was on the lower side. Now,
Excuse me, sir.
yes, sir, please.
Sir, if the nose angle, if at all, if we keep on increase, normally will the cavitating length will increase or decrease, sir? Cavity
Yes.
length.
Yes, please. So now it's a very good question. Now look at the nose from three aspects. And for this, let me go back. So if we, for example, if we start here, one tangent you draw, one tangent you draw, so that gives you the angle of entrance. Now let's start with a very low angle of entrance. That means when you have a section which is highly conical in nature, keep on increasing the angle of entrance, and finally you will get a body in which it can actually become very blunt, and that becomes the bluff body. So when you talk about a cone, then if the water is entering here, it will have a very less chance of getting away from the body of the vehicle. That means it is very likely that it will follow, and if at all it's separate, it will separate somewhere here. That means if the angle of entrance is low, the flow will have a tendency to follow the body of the surface over a larger length rather than when you have angle of entrance is extremely large and the body becomes bluff. When the body becomes bluff, then the flow may actually separate right here. So it will enter here and it will come back. It will enter here, it will come back. So this body will affect your drag adversely. And because of this, it will have less influence on the power side. Now, when it comes to cavitation, now cavitation will happen if the fluid velocity here is on the larger side, not because of the flow separation, but the chances of flow separation will ensure that this particular area and this particular area remains under fluid particle of very high velocity. So when it comes to bluff body, that means when this area becomes larger and larger, you will have very less area which is subjected to cavitation. But the chances of cavitation happening will reduce significantly. In terms of conical body, when you are trying to run the body at very high velocity, then the chances of cavitation will actually go down. But if it happens, then the larger body will be subjected to cavitation. So now, think in terms of design. If you have a body which is likely to be subjected to cavitation very often, in that case, it is not advisable for you to design that body with conical section. Because if it happens, then the large body will be exposed to cavitation. When it comes to the chances of cavitation being very low, in that case, you design with a very bluff section because even if it happens, in that case, the very little area is subjected to cavitation. Now, when you design cavitating sections, for example, supercavitating section, then they are likely to have very narrow, sharp conical section. When you design cavitating section, they are likely to have fuller and fuller shape. When you design subcavitating section, they are likely to have much more blunt edges. So, subcavitating, cavitating, supercavitating. The supercavitating sections will be very narrow, very sharp, like a conical section. Cavitating sections will have a combination of conical section and the bluff body. That means half full and half fine. When it comes
Sir, sir,
to,
in
yes,
sir, in supercavitators,
yes,
normally, as you said that we are going to consider very sharp bodies.
very sharp.
Does the angle really affect the cavity length and cavity diameter so that the bubbles are going to get affected, sir?
Yes, of course. See, because you do not want very large area to be exposed to the cavitation, you are ensuring that the edges are very kind of pointed, so very little area is exposed to the cavitation. Now think about it. You have a propeller which is uh, almost like a blade, the fan of the blade, which is very blunt. Now, if the whole area is exposed to cavitation, it will corrode. And if it starts corroding from there, then the thrust delivered or everything else which is delivered from the hydrodynamics perspective will actually come down. So length of cavitation, the the profile of cavitation, and the pressure distribution which will be happening over the body, it depends upon what is the length, what is the tip, and how this length and the area is varying over the shape. So if you have a body which is extremely long and the base diameter is also larger, and then you have the larger diameter continuum, this body cannot be used when it comes to supercavitation, because the moment it is exposed to supercavitation, the body will start corroding at the tip, which is a very large area. And this very large area will start propagating inwards. And in that case, it will be difficult for you to control the cavitation and your whole system will fall from the baseline. When it comes to the other, that means when we are ensuring the tip is very small and the base is very large, and we are tapering it in a very kind of, you can say, the fair manner, that means not in a parabolic fashion, but in a linear fashion. In that case, even if you assume that the tip is damaged because of cavitation, the damage will not propagate inwards, that means towards the base. And that will protect your entire structure. That will, if it is propeller, it will save your entire propeller plate. So this concept is something which remains true when it comes to, you can say, the propeller blades operating in air and propeller blades operating in water. So even in the field of aerodynamics, if the flow is subjected to very high RPM, then the tip is likely to be very narrow. When it is subjected to lower RPM and when you do not have the chance of cavitation, in that case you will try to make it as wider as possible. But understand this very clearly that except this supercavitation, normally you do not prefer the pointed blades because they affect the thrust adversely. They do not deliver the thrust which you need. But the design argument is slightly different. If I want cavitation to happen, I will want my entire body to be under cavitation rather than only a part of it under cavitation. Because subcavitating structures or subcavitation propeller have other complications. Well, for example, what is the biggest advantage of, for example, cavitation and all that? They have something good when it comes to the drag, when it comes to the thrust, when it comes to the power and all that. But from design perspective, ensure that if it is subjected to cavitation, let the entire body be under cavitation rather than having only a part of the body under cavitation. That's where the super cavitation comes into. We normally want to avoid cavitation. Similarly, when it comes to vortex induced vibration and all that. But in certain areas, it is desired to have them. Any other doubt?
Thank you, sir.
Okay. Feel free to ask whatever questions you have. So we were discussing this that the location is changing, the shape is changing, the size is changing. This is some pictures we have shown. What is evolving over a period of time is that the size is becoming sleek, endurance is going up, the propulsion is getting mixed. That means diesel diesel electric, nuclear propulsion. Deep depth operations for all kind of structure, it is very important that the depth is increased over a period of time. Submarines were designed for around 300, 400 meters. Now they are designed for 500, 600, 1000 meters. The remotely operated vehicles, the deep submerged vehicle, now they are designed for 3000 meter, 5000 meter, 10,000 meter. The largest depth ranked ROV in India is being designed by NIOT, one of our sister organizations, National Institute of Ocean Technology. So they are designing it for 6,000 meter, and they are also planning that next from 6,000 they will see 800 to 6,000 meter, how the design is evolving over a period of time. So one is that the hydrostatic pressure. One good thing is that the deeper you go, the wave effect will vanish, the current effect will vanish. So it's only about hydrostatic, but that's not really that simple because you need to design structures which can withstand that much hydrostatic pressure. Compression gives rise to buckling. That means structures are susceptible to buckling when the compressive forces are large. I explained about the concept of buoyancy and weight. That also is critical because you cannot rely all the time on thrusters. They're very expensive to operate, very expensive to maintain. So you need to have other mechanism by which the buoyancy can be changed. Propulsion, all about diesel when it comes to ship, all about diesel electric or nuclear propulsion when it comes to submarines or the battery powered vehicle, underwater vehicles. So all the things which you can think of in terms of propulsion are actually coming into design when you think of underwater vehicles. Now this is general arrangement. Now when it comes to design of a ship or design of a submarine or design of an underwater vehicle, the idea is to design a system that is able to support and transmit the load and forces to the support. So one essential thing is that for us the weight is supported by buoyancy. So that's one good advantage we have. If the body is submerged, in that case the whole volume of the body gives the volume of water or volume of fluid displaced multiplied by the density will give you the buoyancy. If the body is surface ship, in that case the depth of submergence will tell you how much is the buoyancy. And the body may be long, body may be short. So you have boats which are less than 30 meters. If it is more than 30 meters, it becomes a ship. And from 30 meters, we have gone up to 400, 450 meters long. Larger ships are around that, 300, 400 meters long. For that length, it becomes a floating beam. So we have a beam which is floating, and this beam is subjected to wave forces. The beam is subjected to the forces coming because of current, etc. Now, to ensure that this beam has sufficient strength, sufficient stability, because the body is floating, the body may be submerged, the body may be deeply submerged. So, if it is floating, in that case, what is the center of flotation? What is the center of gravity? What is the metacentric height? Is the GM. If it is surface ship, GM should be positive. If it is deeply submerged, in that case, it starts reducing. Then the economic value, that means whatever system you design from the hydrodynamics perspective, it should have low drag. Low drag should be converted to low power. The low power should also ensure that it is having low operational cost. Now, this hydrodynamic concept over the entire length should be made available in terms of a structural system. A structural system will have many smaller structural subsystems that work together to provide a strong, stable, and cost effective structure. For example, you cannot have a beam of 400 meters. You basically will have sections of few meters welded together. So that means you have many subsystems that will be combined, that will be welded together to give a large structure available to you. When it comes to underwater vehicles, you have autonomous underwater vehicles, you have submarines, you have remotely operated vehicles. Remotely operated vehicles are thruster driven. They do not have propeller of their own, so they are governed by thrusters. So they have multiple thrusters in multiple directions. So they are lowered. They can move from one location to other location, but everything will be dependent upon the thruster. When it comes to autonomous underwater vehicle, they will have propeller of their own, and this propeller will be used for moving the vehicle forward. They will also have thrusters, and the thruster can be used for maneuvering. The thruster can be used for depth control. Then you have ship which will have its propeller. There's also a class of vehicle which are smaller, which will not have propeller, but they will be free floating. It means depending upon the current, depending upon the waves, they will move from one location to other location. They are called gliders, normally less than 1 meter. Submarines, if you look at the shape, they are circular because of the hydrostatic pressure. Stiffened, they are framed. So all three structures which we have talked today, remotely operated vehicle, submarines, and autonomous underwater vehicles, they are stiffened, they are framed. Approximately 40% of the focus and priority will be given to the structural design. 30% priority will be given to the hydrodynamic design. 30% priority will be given to the operational design. So it is 30, 30, 40. 30% comes from hydrodynamics, 30% comes from operational flexibility, operational design requirements, and 40% becomes the structural part. Now, it is also important because when the depth of submergence goes up, then your chance of survival if something goes wrong actually reduces. So if something goes wrong at 3000 meters, it becomes your death rate. And something goes wrong at 5000 meters, it becomes. Submarines, when they are exposed to accident, then the accidents are quite fatal. Means it's really nothing can be done because the structure will collapse and such a hydrodynamic depth, compressive loads will be higher. Once the structure starts buckling. So, from the depth perspective, the main issue is the hydrostatic pressure. And the pressure hull is the primary structural component of the submarine, particularly the collapse depth at which the complete failure is expected within a narrow range. Now, collapse depth is computed as maximum operable depth or service depth multiplied by the factor of safety. Now, factor of safety is taken as 1.5 to 2.5. For diesel electric submarines, the low factor of safety is used. Nuclear power submarine, high factor of safety is used. And design hydrostatic pressure is always computed at the collapsible depth. That means if you say the collapse depth is 10,000 meters, then the hydrostatic pressure is actually 10,000 meter multiplied by the rho and g. Loads on submarine, this is something which is important because All of them have basic origin in the field of aerodynamics. One is explosion. Now, for example, you have a structure which is floating underwater. You may have a mine, you may have volcano, or somebody may have fired a missile. Now, this missile or this mining or this volcano may introduce something which is explosive force by nature. Pressure generated by bursting of large underwater gas bubbles. All can happen. Now, when we have a force which is coming from impact, then it is important for us to know for what duration it is. Whether it is exposed for a large duration, whether it is exposed for a shorter duration. If it is exposed for a larger duration, then what is the value of the force? And then it can generate waves, and these waves will propagate because you are operating underwater. So that's where the hydrodynamics comes into picture. This can give you what noise, it can give you vibration, it can give you a lot of other complications. Now, a structure which may not fail otherwise may fail in the explosion. There may be temperature change. There may be other complexities which will be given rise to in case of any explosion. In surface condition, when it is close to the surface, you have only structural loads coming into picture, which will basically give you the bending. You will also have the transverse shear forces which are coming into picture, and you will also have the torsional loads which are coming into picture. Now, where the torsional loads are important. Now, think in terms of a container vessel which is carrying containers on board. It's a ship which is open, or think of a ship which has large moon pool through which the drilling will be done, and it is subjected to oblique wave. There is a structure like this, the wave is coming like this at an angle, it will introduce torsion. So ships which have some kind of opening in the hull, and this opening may be because of the requirement of carrying container on board, on deck. It can come because of the moon pool. It can come because of other issues. Under the condition of oblique wave, it will have very high torsional loads. Now, submarines will always have some opening in the hull because that's where you will enter. Similarly, autonomous underwater vehicles will have some opening in the hull because that's how the system will be put inside. Similarly, remotely operated vehicles, they are like box structures. They will have, all of them will have opening in the hull. Any opening when you are close to the surface, you have oblique wave will give you torsion. Local loads will fall either in the longitudinal buckling, longitudinal bending, or in the torsion vibration. Design guidelines when it comes to underwater vehicles, the first thing you need to ensure is that the vibration should be low. Because if it is, even if you assume that it's autonomous underwater vehicle, no human presence, the vibration adversely affect the performance of sensing. So if you have sensors on board, vibration will adversely affect the performance of sensors. So low levels of vibration are important, extremely important. Hull in the dived condition. So you have autonomous underwater vehicle launched from the surface. It will go down. That is called diving mechanism. How it will dive? The weight will be kept on the higher side. The buoyancy will be kept on the lower side. So the vehicle will start sinking. That's called the diving in condition. And in this case, when it is at the surface, the compressive stresses are low. When it starts going down, the compressive stresses starts increasing, and that's where the longitudinal compressive stresses comes into picture. And it is normally half the magnitude of the hoop stresses or the circumferential stresses which are coming into picture. The hydrostatic pressure, as I explained before, is computed at the depth of collapse. And that's what is the external pressure. So if we want our autonomous underwater vehicle to go at 100 meter, it's 100 multiplied by rho in g. If it is 1000, it is 1000 multiplied by rho in g. There's a huge difference between 100 and 1000. And water is highly dense, highly viscous. Minimum thickness of the pressure hull, external pressure multiplied by the radius of pressure hull, divided by the 2 times of yield distance of the pressure hull material. Now, the critical observation is that whenever we design of a underwater vehicle, or whenever we think of anything which can go deeper and deeper, the larger diameter, which will come because we have just seen that structures are getting larger, structures are getting speedier, that means the average speed is going up. So larger diameter means that the plate thickness will actually go up, even for a lesser diameter. And it is important for you to hover around certain L by D. So most of the underwater vehicles, most of the systems which are operating at a particular hydrostatic depth, the L by D normally will vary between 5 to 8. So if you have a length of 10 meter, then you can calculate using 5 and 8 what is the minimum diameter, what is the maximum diameter possible. So within that 5 to 8 range, you have to find a solution. Now, this 5 to 8 is also dependent upon what kind of velocity you have in mind. The lower velocity means that the drag is less significant. The higher velocity means that the drag is more significant. So if the drag is more significant, then it is better for you to design a body which is long in cylinder. When the velocity is low, and in the field of naval architecture, and when it comes to the underwater vehicles, normally the operating velocities are between 1 meter per second to 3 meter per second. So it is not advisable to design anything less than 1 meter. It is also not advisable to design anything more than 3 meter per second. So 1 to 3 meter is something which is reasonably fast or reasonably required system design. Less than 1 meter, you can design a body which is extremely fat and extremely short in diameter. The body becomes more and more full. When it comes to more than 3 meter per second, you need to design body which is extremely long, extremely narrow, which becomes long in cylinder. And between 1 meter per second to 3 meter per second, you stick to 5 to 8 L by D ratio and design it accordingly. The minimum thickness of the hull can be reduced if we go for material with high yield strength. A lesser thickness is advisable because it reduces the weight, the dead weight of the structure. And when it reduces the dead weight, the payload will actually go up. But normally, when you say higher yield strength, the cost actually becomes larger. Now, some of you will have some background in the field of material science. So think in terms of 4 or 5 materials which are normally available. Steel, steel alloy, composites, titanium. Now, titanium is very light. The yield strength in compression, the yield strength in tension is also significantly large. Think in terms of composites. Compressive yield strength is very large. Tensile yield strength is very low. Steel, reasonably high compressive yield strength, reasonably high tensile yield strength, abnormally high modulus of elasticity. When it comes to modulus of elasticity, you don't get any improvement beyond steel. Titanium, no improvement. Composites, much less. Even the steel alloys, which offers you improvement in the compressive yield strength or tensile yield strength. They also do not offer any improvement on the modulus of velocity. Now, because of this, when it comes to underwater vehicles, steel is preferred. Other complications, titanium, it's very difficult to weld. You need electronic beam welding, expensive, cost is extremely large. So only one underwater vehicle, one submarine was tried with titanium, that was Russian Navy. No other navy ever thought about it because the idea itself is not really pursuable. So think in terms of buckling, think in terms of tension, compression. Buckling is governed by modulus of elasticity. Tension, compression is governed by the compressive yield strength or tensile yield strength. So any structure which is susceptible to buckling will have dependency on the steel because steel offers you the best modulus of elasticity. Pressure hull absorbs all the forces in the longitudinal direction without the requirement of a transverse ring stiffness. However, the shell is stiffened by ring stiffness so that it can also absorb what is called circumferential stresses originating due to buckling loads. Now, also understand that when it comes to current, when it comes to waves, they are likely to introduce not only the longitudinal stresses but also the transverse stresses and the circumferential stresses. For example, if you have current, if you have wave, the wave combined with current will actually introduce the circumferential stresses. Ring stiffeners are normally of T section and they are welded to the pressure hull shell, and the entire system will act like a unit. The hydrostatic pressure, the pressure coming because of the sheer presence of water, is important. It's linear variation. Now, transverse frame will give you the structure which is likely to behave like a skeleton. That means the part which will be resisting the compressive forces maximum. P absolute is P atmospheric pressure, rho gh. Here we have used rho g z. The pressure rises, for example, 3 atmospheric pressure to 44 psi per 100 square feet. Only pressure hub has to support this pressure difference because the main ballast tank and the superstructure will not be supporting the hydrostatic pressure. Now, the manufacturing capability is something which is dependent upon the kind of practices you are following, kind of material you are using. It is important because we are talking about a structure which is expected to be fair, which need to be circular, and any deviation from this circularity will actually introduce areas which will have very high stress concentration. So, if we have a hydrostatic pressure acting on a circular section, and any deviation from this circular section will give stresses varying somewhere from 30% higher to almost 70, and to depending upon what extent you have gone out of circularity, 1.25 to 1.5 times of the normal stress. So think about it, 30% to almost like 75% to 100% can happen because you are not able to ensure that the section is perfectly circular. Inner hull of submarine should be designed to have pressure sensitive equipments. Outer hull. Now, is what I wanted to discuss. Smooth fairing of the hull from nose to paddle middle body to the tail. Now we have just discussed about the nose. We have discussed about the tail. Tails are normally of slightly larger length. They also affect the stability. Now just see the shape of a bullet. Bullets will always be designed with very full tail. Their nose will be something like this. It means it is faired over a very small length. Depending upon what kind of guns you want to fire, this shape will change. And that tells you at the bullets which are fired for a very high velocity will try to have slightly longer nose and all that. What here we want to focus upon is that you have broadly three areas: nose, tail, and the middle body. How they are faired into each other, that also is important because the ideal hydrodynamic body or the ideal hydrodynamic shape is that where there is no boundary layer separation, where the fluid enters the surface and it remains on the surface over the entire length of the body. Now, this is something which is not true if the body is not faired properly. So, if you have nose, if you have the middle body, and the nose is very long and narrow, and the body is full, and you have just tried to fair it over a very shorter length, it gives rise to what we call hard shoulder. That means the shoulder of the body is becoming hard, and that will give rise to the flow separation. So any body which has hard shoulder will actually have very large drag. So ships are designed to ensure that there is no hard shoulder. Similarly, when it comes to the underwater vehicles, they are designed in such a way that the nose should get properly faired into the middle body, and in middle body is also faired properly to the tail of the body. Now, if you see tail here, if you see the middle body here, the tail has been faired linearly. It's, it will give rise to a conical variation into the middle body. Here, the nose is integrated into the middle body non-linearly, and this will give rise to what we call parabolic variation. So both are popular. On the tail side, normally we use the linear variation, the conical section, because of the presence of propeller. Here, we want to ensure that the areas are utilized also for the area for the volume. And if we cut it like this, it becomes a conical section, and we will see that this much area is lost, this much area is lost. So smooth fairing is important, and also important to ensure that there is no flow separation, there is no increase in drag. Ballast and trim tanks are accommodated properly. High strength not required, so made of mild steel and fiberglass. That means the sections which are not really exposed to the hydrostatic pressure. MBT is the main ballast tank, the largest tanks, apart from the sections which are used to house the missiles and all that. Main ballast tanks are the largest tanks. You also have the depth control tanks, which will come into play when you want to increase or decrease the depth of operation. That means when you want to dive in, when you want to dive out, the depth control tanks are utilized. Longitudinal bending, just a summary of whatever we have discussed so far. Longitudinal bending is subjected to length of the vehicle, whether it is close to the surface. In that case, the force will come because of wave. the force will come because of current. If it is below the mean sea level, if it is below the water surface, in that case, the forces are likely to be coming purely from the hydrostatics, not from hydrodynamics. Hogging and sagging, that means bending positive and bending negative, will give large variation in the compressive and tensile stresses away from the neutral axis. And when you have large variation of stresses, and that too because of the presence of current, because of the presence of wave, which are also not a very stationary phenomenon. For example, when it comes to current, when it comes to wave, they also have certain randomness in their behavior. So that randomness will introduce reversal of stresses also in a random fashion. So when you have reversal of stresses to a large extent in a random fashion, then the fatigue also becomes complicated. Fatigue also becomes complex. So underwater systems, underwater vehicles, underwater structures, all will be designed, all will be analyzed for a fatigue requirement because of the reversal of the stresses. Now, when it comes to shape, for example, cylinder is very good for buckling. Cylinder is also very good against what we call reversal of stresses. That means the fatigue resistant design. But cylinder is unfortunately not very good for bending. So hydrostatic pressure is manager is very important for submarines, very important for underwater vehicles. Water pressure attempts to implode ship because the structure will start having large amount of compression coming into picture. Transverse strains are needed to combat the loading. That means basically the idea is to reduce the effective span. So from the hydrostatics perspective, it is important for you to reduce the unsupported length or what we call the span length. From the hydrodynamic perspective, it is important for you to ensure that large area is not subjected to whatever forces you are encountering. So flow entrance, flow angle, angle of entrance, fairing, all these things becomes important. Transverse frame will be required to combat the loading, and cylinder is a very good pressure vessel. Now, this I was talking about what are the materials available, different materials, and I explained that there is no replacement for steel, and here you can see the reason. There are different materials we have listed. For example, A, B, C, D, E. See here, it's aluminum alloy. See the density, very low. See the compressive yield strength, 414 megapascal. And most of the metals will have the same compressive yield strength and tensile yield strength will be the same. See the elastic modulus, pretty low, 72.4 only. Steel alloy, 7850. Compressive yield strength, 951, significantly large. Modulus of elasticity, 205. Steel, ordinary steel, mild steel, A36. Density, 7800. Compressive yield strength, 250. And elastic modulus, 200. C carbon fiber, C e-glass fiber, C titanium alloy. And see, there is nothing which goes beyond 200. And that comes with extremely easy welding, extremely easy way by which it can be joined, it can be manufactured, different sheets can be generated of different size, different shape. And because of this, sections which are designed for particular requirement, for example, compression and tension, buckling will be of a steel. Sections which are designed primarily for compression, no tension, they can be made of e-glass fiber, they can be made of carbon fiber. Structures which are not designed for buckling, compression yielding, tensile yielding. Only the density is important. That means you want the structure to be light. They are made of aluminum. So now think of aircraft. You have very high velocities. You have very less density of air. You have very less viscosity. So from aerodynamics perspective, it is better for you to go with aluminum. From hydrodynamic perspective, it is important for you to go with steel. From hydrostatic perspective, that means when you are designing the structure only for compression, you can go for carbon fiber, you can go for E-class fiber. And titanium is something which is light, extremely large compressive yield strength, but not really so good elastic modulus. Now, this is also important because we were talking about hydrodynamics, we were talking about hydrodynamic force coming on the hull. So when you have buckling, when you have torsion, when you have torsional buckling, then it is possible that you may have cracks which will develop over a period of time. Similarly, we are talking about structures which are welded together. We cannot have a one sheet or one plate or one beam dominated design. So welded connections are likely to have some kind of fracture, some kind of crack over a period of time. Now, this crack, if it is subjected to tension, the crack will have tendency to get widened. In case there is a compression only, the crack will not widen. So it is important for us to understand what is crack width, whether the crack will propagate over a period of time or not. If it is propagating over a period of time, then what is the propagating velocity? Because crack, once it starts widening, in our case, the stability, the hydrodynamic stability, the buoyancy, the hydrodynamic buoyancy is coming because the structure is intact. If it is not intact, if water can enter, in that case, the buoyancy will be lost. If the buoyancy is lost, the weight is not supported because we are not on a ground where the weight is supported by the foundation. Here, the weight is supported by buoyancy. The moment buoyancy is gone, the structure will start sinking. So, crack and how the crack propagates, what is the crack width, whether the crack is widening or not, that is extremely important for underwater vehicles. So, you have a crack, see here. If you try to compress it, you will have compression closing. Not really scary, but think of a crack, think of a tensile force, then you will have tension opening. You have a crack, now apply shear, and this shear, especially when it is in plane, that means you are applying shear which is in plane of the crack. It's not really dangerous, safer. But when you have shear which is out of plane to the crack plane, in that case it becomes damaging. It becomes scary because the crack will have tendency to get widened. So it is important for us to understand crack width propagation, crack velocity. Now, few slides before we were talking about explosion. We were talking about implosion. We were talking about the forces which will come because of impact. Now, all of them, impact, explosion, they are something which are likely to introduce crack into the structure. And if the crack is not attended properly, if the crack is having a tendency to get wide enough, in that case, the whole structure will collapse. Think of it, this is a plane is strained, you have a crack. In case of plane is strained, the crack will only have tendency to travel in a particular direction. That means only a particular dimension will go up. So crack width may go up, crack length may go up, but not really the crack area. So crack under the condition of plane strain is less dangerous rather than crack under the condition of plane stress. Because in that case, the area of the crack affected zone will actually go up. Now, these are failure modes which I can skip. So let me see if I have.
Sir, thank you very much, sir. I request all the participants, if you have any queries, you please ask, unmute and ask. I request all the participants. Sir, is it over, sir, your presentation?
No, I wanted to discuss something else, but I just saw the time is almost 8:30. So,
Okay, sir. Thank you, slides. By seeing, I just am calling. You please continue, sir. No problem.
one more idea I want to discuss with.
Sir, please, please.
Can you see the slide?
Sir,
Yes, sir. Yes, sir.
Yes. So I was talking about the shapes. So this is a couple of slides I want to discuss with all of you. Now think about a sphere. What is the advantage of a sphere? The most favorable weight to displacement ratio. What are the disadvantages? It's a difficult and inefficient interior arrangement. That means you cannot think of a sphere which can be properly packed. The through-hull penetration is also easily made. Stress analysis more accurate and less complex. The moderate weight to displacement ratio. Large hydrodynamic drag. So if you want to run a spherical body inside the fluid, the drag penalty you have to pay is extremely large. Ellipse, better than sphere, more efficient interior arrangement than a sphere. Through hull penetration is easily incorporated, inexpensive to construct. The disadvantage, expensive to construct compared to other developable shapes. When it comes to developable shape, we have example of cylinder, we example of cone, example of a truncated cone. All of them can be made very easily with simple mechanical means. So that's the concept of developable surfaces and non-developable surfaces. Non-developable surfaces means that material will require thinning or thickening in the manufacturing process. That can be done by only heating or compressing the material. Very expensive. So a sphere is a typical case of non-developable surface. If you want to generate a sphere, in some section the material will start thinning, in some section material will start thickening. When it comes to cylinder, when it comes to cone, they can be made just by rolling, pressing, and bending. So the manufacturing processes are very simple, very cost effective. Cylinder, most efficient interior arrangement than any other similar shape. For example, compared to sphere and ellipse, cylinder is much better when it comes to interior arrangements. Very low hydrodynamic drag compared to ellipse and sphere. It is slightly complicated when it comes to the weight to displacement ratio. Also, the interior frames are required to increase their strength, which are not really needed when you talk about a sphere. Here are the material properties. which we normally consider in design, corrosion resistance, stress to weight or stress to density ratio, resistance to what is called stress corrosion and cracking, resistance to low cycle fatigue, creep resistance, stress relief embrittlement, resistance to brittle fracture, high strength to density ratio. Now, all of them are related to hydrodynamics. That's what I said in the beginning itself that we stress upon this point very, very often and very forcefully that never think hydrodynamics independent of material science, structures, and other areas. Now, water is viscous. Water has very high density. You have primarily presence of seawater, which is highly corrosive. You have a water which can be entrapped with air. The air can be polluting. Now, all of them, for example, when it comes to pH, when the pH is less than 7, the water becomes acidic, which normally is the case with seawater. Seawater is highly acidic. It will likely to corrode the structures very easily. So, the more wave action you have, the more current action you have, coupled with pH, they will actually worsen your corrosion environment. High ductility, because you have the structures which are exposed to reversal of stresses over a very long period of time. Ductility comes into picture. You have structure which is exposed to fracture, structure exposed to impact, so fracture comes into picture. Weldability, you have structures which are long enough, formability, etc. And that's what we have said here, despite its weaknesses such as brittleness, high sensitivity to surface abrasion, considerable strength degradation at joints, glass and glass fibers have very low weight to displacement ratio. That's the only thing which favors them. These are the battery options. Now, this is something which I wanted to show to the audiences because we have research in this area quite a lot. Now, mathematically, how do you define shape? Here we have said that the nose and the tail and the middle body. So this is tail, primarily dependent upon what is the requirement of the stability, how you want the propeller to be adjusted here. Now, in case there's a propeller, we truncate it somewhere here and we allow some d minimum here. That is basically to account for the shaft of the propeller and all that. So this is called length of tail, this is called length of middle, this is called length of nose. And then you have the radial nose coefficient, then you have the d max and the tail radial coefficient. That means how do you vary the tail? These are formulas which are given mathematically to design the tail and nose. And T and NN, they are the nose shape variation coefficient, tail shape variation coefficient, and they are taken from 1 to 5. And ideally, we get whatever we want between 2 and 3. That means when we optimize, the optimum range of NT and NN comes around 2 to 3. D max by 2 is the maximum radius available over the entire middle length. And then the radius starts coming down close to 0 here and close to 0 here in the tail end. L to D max is roughly between 5 to 8. I have told you this before. And when it comes to hydrodynamics, when it comes to the velocities and all that, between 1 to 3, this is the ideal ratio. Less than 1 meter, you can actually go higher than 8. When it comes to more than 3, it is advisable for you to go less than 5. Our extensive optimization of the studies which we have done, LM is approximately 40 to 60% of the length. Length of nose is approximately 10 to 20% of the total length, and tail is around 20 to 50% of the total length. Prefer a full nose and fine tail. Now, this gives you whatever you want on the propulsion side. This gives you whatever you want on the resistance side, the drag side. This gives you whatever you want on the payload side. That means the area and the volume which you want to carry. And this combined with propeller, what is the diameter of the propeller? Because, for example, diameter of the propeller is not expected to be higher than the Dmax. So once you fix Dmax, the maximum diameter of the propeller which you can accommodate will be fixed. Similarly, when you fix the length of middle, you cannot have a length of tail which is higher than the length of middle. So that means proportionately when you fix the length of the body, everything else will be fixed almost, and then you have a kind of range on which you can optimize the different length and the different radius and try to get whatever payload you want, whatever volume you want, whatever power to resistance ratio you want, and all. So mathematically, that's how it looks like. So I will close here. All these notes will be circulated to all the participants. In case you have any doubt, you can come back to us. You can write to us. You can WhatsApp me, and we are always free to offer whatever little advice we can give you on your research problem, on your any other problem which you are encountering. Feel free to write to us. We are very open for discussion in the sense.
Yeah, thank you very much, sir. My dear participants, including Santosh, you please raise your queries so that our sir will tomorrow he will enhance his topic. Sir, wonderful topic you have given. So first time we are listening, sir. Actually, uh, H.N. Das sir suggested you are doing research on this.
Yes.
And wonderfully you have taught the topics, and also this IIT Madras expertise also helpful. I request some of the participants to raise your questions. And tomorrow our topic is high computational performance in hydrodynamic design. Sir will deliver tomorrow the same way.
My question is, sir, basically, whether we do the numerical analysis or the experimental work, sir, how do we calculate this cavity length or cavity diameter, sir?
Yes. Now, what is important are the three. When it comes to the numerical side, the scaling is not important. That means you can actually run the full scale model in the numerical analysis, the numerical model. The problem is that when it comes to the experimental setup, it is difficult for you to maintain the scale. You cannot maintain what is scale. When it comes to lowering the scale, that means when you are trying to reduce, for example, I have a propeller which is roughly 10-meter diameter for a container ship. I cannot make a 10-meter diameter propeller and test it in the cavitational tunnel because my cavitational tunnel width, length, and the diameter all are restricted. So when it comes to cavity length and the cavity diameter, what you get from the numerical is something which is coming with approximation, which is coming with whatever everything else you have done in the numerical modeling. When it comes to experimental side, the cost is up, and you are getting the gravitational length and the gravitational the diameter only for a scale structure, not really on the full scale structure. Now, how do you relate these two designs? That's really difficult, and that is something which, especially when it comes to issues like cavitation, has not been really well understood. One more issue is that it's all about what is the RPM and what is the fluid velocity you have. basically these are two parameters which are most important when it comes to cavitation. When you start rotating something at a very high RPM, and when you have the fluid velocities which are very high, then the issues which come because of the noise and the issues which come because of the vibration, and they are also introducing waves which travel through water medium. All of them interfere in your experimental work. And when you want to correlate the experimental work with the numerical work, it is not matching because you have disparity in the scale, you have disparity which is coming because of noise and vibration, and how this noise and vibration is giving rise to the sound waves which are traveling through water as a medium. So, in my understanding, that's what we advocate, at least to all of our participants, that when it comes to hydrodynamics, you have to focus in our understanding on the full scale. And that's where the CFD has entered a big way, the numerical modeling has entered a big way, because at least you can say with higher performance, with higher computing, with higher speed, you can actually run a model which is close to the scale you want. But in experimental side, it's just not possible. So your experimental results are reliable, they are valid, everything is fine, but also understand that they're applicable only at a reasonably low scale of model. You can manufacture, you can design. And I have seen, especially in terms of cavitation, the kind of facilities we have, they are on the much lower side than the actual structure which will be encountered. So cavitational length, cavitational the diameter of the cavity and all that is important for you to investigate much on the CFD side rather than on the experimental side. That is much more, you can say from design perspective, that is much more accurate approach to us. What we are investigating in our department, in our institute, is that what happens to the noise? Because one way the, the field is evolving is that all of these features, for example, hydrodynamics of vessel which is coming to the port, hydrodynamics of vessel which is coming to restricted water, running through a lake, running through, all of them are essentially affecting the marine environment close by. And over a period of time, we have seen the fish movement goes up or it changed from one location to another location. So noise related to cavitation is something which is gaining importance, which was not there a couple of years before. And the reason is that everything else depends upon the noise, especially when it comes to the health of marine environment. It is, it is all related to noise. So hydro, acoustic, and vibration. These are three things which we need to combine to understand cavitation in a proper perspective. Currently, the more focus is there on the hydrodynamic side, very less focus is there on the acoustic side, very less focus is there on the vibration side. But understand this very clearly that cavitation is a hydrodynamic process, but it has very serious consequences when it comes to acoustics and also when it comes to vibration. The day we can combine acoustics, hydrodynamics, and vibration into the experimental setup, our results will be much more reliable, even with slightly lesser skill ratio. That's broadly what I see the area. Anything else?
So, good evening, sir. This is Rakesh Kumar, Assistant Professor from Indian Maritime University, Chennai campus.
Yes.
Sir, I need to I have a query related to fracture phenomena. Sir, could you please let me know, is there any study or analysis of fracture phenomena in marine vehicles? Like, if the research is going on, then will they consider the hydrodynamic loads on the marine vessels to study the fracture phenomena, or is there any fluid structure interaction phenomena also comes into picture?
Yes. So, and see, what happens if you have fracture, it can happen because of multiple reasons. But the presence of water, For example, you have a wave which is generated, and the wave will propagate, and this wave will propagate with certain velocity, and this is something which will give rise to the fatigue, and this will also give rise to the force or the pressure which will come. Now think about it. You have a force which is coming up, which is dynamic in nature. So you have a wave which is coming to you, dynamic in nature, and it will keep on happening. So when it comes to fatigue of underwater structures, fatigue of underwater pipelines, risers, and look at them in one go. Now, don't think that riser is something different from a vehicle. Vehicle is different from platform. All of them are same because all of them are subjected to a kind of force which is dynamic in nature, which is random in nature. So fluid will have a structure component because you are dealing with a fluid which is dynamic. You are dealing with a fluid which is of very high density. You are dealing with a fluid which is of viscosity. This all three combined together will give rise to fatigue, and fatigue will give rise to crack, and crack will propagate. Now, our own work in this field has been done on risers. So we have done a lot of work on marine risers, how the marine riser uh, is affected by fatigue coming because of the current. Now, fatigue in general in the naval context is more driven by the current, less driven by waves, and less driven by other factors. Now, think about it: riser, which is subjected to current, riser is also wave. Now, if you have a structure where there is no wave effect, there is no current effect, in that case, there is very little chance of fatigue coming into picture because there is no reversal of the stresses and there is no cyclic load. So remove the cyclic part from it, remove the reversal of the stresses. In that case, the fatigue comes down drastically. If you have, for example, ROV doesn't have reversal of the stresses. It doesn't operate very close to the surface. That means it doesn't have wave effect. It doesn't have current effect. So there is no fatigue coming to it. Autonomous underwater vehicles, they are launched from the surface. So they are exposed to current. They are exposed to wave. There will be effect of fatigue coming to it. Platforms, riders, they operate close to the free surface. So they will have very large fatigue coming because of current, because of wave. So think in terms of the structure, think where they are operating, think whether they are subjected to cyclic loads, reversal of stress, and then you derive whether the fatigue will be an important feature in their design or not. So in this field, extensive work has been done on risers platform, very little on autonomous underwater vehicles because the autonomous underwater vehicles is a very new concept, not kind of the way the risers have been done or the ships have been done. And also understand that the vehicles are smaller. The largest AUV which people have designed, people have thought is only 10 meter long. They are much smaller, much like properly designed shape, properly designed stiffeners, properly designed longitudinal beam. But yes, once it hits the torpedo, it's all like gone case because the impact is very large. Impact very large means crack will be very large, and the crack is very large means you have the propagation of crack. So, in under special loads, any structure can actually come under crack. But otherwise, ROVs, underwater vehicles, except submarines, which are slightly difficult, they are not subjected to fatigue the way offshore platforms will be, riser will be.
So, is there any hydraulic fracturing kind of stuff in this hydrodynamic study of
Now,
structures?
this is something which is applicable to a very kind of, you can say, a different area. Say in the field of mining, in the field of oil and gas exploration, hydraulic fracturing has been used to a very large extent, successfully. And the idea is very simple. Think, for example, of a tube which is of very small diameter, and the tube is filled with, for example, oil. Now, if the diameter of the tube is very low, In that case, it is difficult for you to ensure that the tube is emptied with oil. Because if you want to capture the oil from the reservoir, in that case, you normally ensure that the pressure is changed and it comes because of the like pressure change, the fluid will start coming out. When the permeability and porosity of the system is on the lower side, it is difficult for you to pump it. It is difficult for you to ensure that it comes out naturally. So in that case, what is the solution? In that case, the solution is that at one end, you start pumping water at a very high velocity. Now, if you have water at a very high velocity and now you are injecting it that to a tube of very low diameter, the velocity will go up further. That will allow your gas and oil to come out mixed with water. Now, when you have oil and gas mixed with water coming to the surface, you separate them and you get the oil and water. So that's the area where hydraulic fracturing has been used very successfully because water has one advantage. It can be used for very high velocities. Water has very high density and not really very high viscosity, which will be there, for example, in other cases. So you have high density, you have very high velocity, you have reasonably low viscosity. And if in case it is pure water, not seawater, it will be less abrasive, it will be less corrosive. So it can be used in all kind of reservoirs. So hydraulic fracturing is something which has been very successful for oil and gas reservoirs, especially when you are trying to extract oil and gas from very low permeable reservoirs or reservoirs with very low permeability. Apart from that, the hydraulic fracturing, water guns and all that have been successfully used for metal cutting because there is no thermal expansion, there is no thermal contraction. Basically, there is no temperature expansion or rise in temperature. The rise in temperature is something which gives too many stresses on the thermal side, especially for metals. So metal cutting. Apart from that, hydro fracturing has very limited application. Now, for example, suppose I want to have a water gun. It's practically impossible for me to cause damage with that hydrostatic, with that gun, because most of the damage for metal is actually done by temperature. So you have explosion, and the explosion is affecting because the temperature goes up. If the temperature goes up, the material will actually cross the elastic limit. It will go to the plastic limit, and when the plastic limit, it will not come back. That deformation will remain permanent into the structure. So hydrofracturing is a successful concept provided you don't need thermal expansion. You need only force coming because of the water current or water stream. Till that, it is useful.
Okay, sir. So my last question, sir, from your knowledge, is there any research community in India who is working or worked in the fracture study of the marine field structures?
Fracture we don't work with. At least I don't work with. I work in fatigue. The fracture so far I have not touched with. But there's a professor in IIT Guwahati. His name is Professor K. Murthy.
Okay.
He's a person who has done extensive work on fatigue. He has also worked extensively on fracture, especially fracture of metal plate, fracture of joints, fracture of notches. So he has done a lot of work. And he has also worked on marine systems, not really marine vehicles, because marine vehicles is a very kind of narrow area. So he may not have worked on this area, but he, as far as the basic fracture mechanism is concerned, and especially when it comes to ocean systems, ocean structures, he has done a lot of work.
Okay, sir. Okay. Thank you very much, sir, for your information.
IIT Guwahati. He's working in
Sir,
IIT.
Okay.
thank you very much, sir. Thank you for sparing your valuable time. I request all the participants kindly join tomorrow before 10 minutes, as sir is coming earlier than us. So you please join at 6:50. Sir, thank you very much, sir. Tomorrow we'll meet. Sir will deliver a lecture on high performance computing for hydrodynamic designs. Thank you very much, sir. Thank you for sparing your valuable time. Namaste.
Thank you, sir. Thank you, sir.
Thank you, sir. Thank you a lot.
Thank you, all the participants.